Welcome back to Differential Equations. This is part 2 of our lecture on applications of first order ODEs. All right, the first part, we went into detail about application problems coming from Newton's second law, F equals ma. For this part of the lecture, we're going to go into detail for what we'll call mixing or flow problems, which we briefly mentioned in the intro, but we'll be building on that now. All right, in the intro, we were very vague in general. We said there was a substance flowing in and out of a tank. To be specific, for our purposes, the substance is going to be salt. And the reason for that is in our mathematical modeling process, we want simplifying assumptions. We're going to choose the substance to be salt because it easily dissolves as well as uniformly throughout a liquid here, water in this case. All right, if we didn't assume that and the substance perhaps clumped together, that would complicate probably some of the mathematical modeling process, and we would end up with likely a differential equation that might be too hard to solve. So for right now, we'll just assume our substance, salt, easily dissolves and disperses uniformly throughout the liquid water here. All right, now there's going to be two quantities that can change. So the first, which is what we're interested in, is what we're going to denote as the function, A as a function of time, and this will denote the amount of salt in the tank at any given time. All right, due to the inflow and outflow, the other quantity that can change is the amount of water in the tank. And we'll denote that total volume of water as V as a function of time. So both the amount of salt in the tank and volume of water in the tank can change over time. All right, so our goal is to get an ODE, which will be a first order, for the amount of salt in the tank at time t, A of t. All right, now we have in red here the very basic net rate of change formula that we stated in the intro, and we're just going to rely on some fundamental ideas learned in your Calc 1 course. A rate of change, we can interpret that as a derivative. So if A of t denotes the amount of salt in the tank at a certain time, the derivative of A with respect to time, what we would write as dA over dt, that then represents the rate of change of salt in the tank. All right, so we're going to be going into detail to figure out kind of expressions for the right-hand side, the rate at which salt enters the tank, as well as the rate at which salt leaves the tank. Now, right now, what we're going to go into detail on is going to seem very complicated. It's going to be a very general mathematical model for kind of a whole host of application problems as you might encounter in kind of more complicated engineering courses. Don't be alarmed and overwhelmed. The actual examples that we're going to solve will be very simple, like we'll see in example 2. So just bear with me. We're going to build a very general equation, and then we're going to basically just get stuff that we're going to plug into that. All right, so let's focus first on the inflow part. So there's salt solution, a combination of salt and water flowing into the tank. All right, what could affect the amount of salt and the amount of water in the tank are two things. There's first, the inflow rate of solution, and make sure you realize it's not the inflow rate of salt, but right now, just the inflow rate of solution. So flowing into the tank is salt dissolved in water in some sort of solution. All right, we're going to denote that symbolically as R. The subscript I denotes the inflow phase, and then this could be a function of time. Now, if this is an engineering problem, maybe you want the inflow rate to change over time. We're not going to go into that much detail, but the model that we're going to build could account for that. All right, the second quantity dealing with the inflow part is C sub I of T, which is going to denote and represent the inflow salt concentration. So you could have not a lot of salt in the solution flowing in which case the concentration is very low, or you could have a very high amount of salt in the solution flowing in which case your concentration would be very high or large. All right, now with these two quantities, we're going to rely on what is called dimensional analysis. You might have done this in a physics or engineering course, but we're going to try to combine these quantities. The inflow rate of solution, we're going to say it has units of gallons per minute, so a total amount of liquid flowing in per time. And then the inflow salt concentration, that will have units of pounds, so pounds of salt per gallon. All right, and what we want to do is find a kind of a way to kind of combine those together to get appropriate units for the inflow of salt. And we would want that to have units of pounds per minute. So pause if needed and see how you might combine those quantities to get that units of pounds per minute. We'll check in a few seconds. All right, now there's not a whole lot of possible combinations here between Ri and Ci, but if we multiply them, the inflow rate times the inflow concentration, take a look at the units. The inflow rate has units of gallons per minute, and then we multiply by the inflow concentration, which has units pounds per gallon. Now, if you just look at this like an algebraic fraction, it looks like the units of gallons cancel out, leaving you with units or dimensions of pounds per minute. That process that we just used here, called dimensional analysis, that's a very useful way to come up with formulas in physics and engineering, but we'll let you go into detail that in those courses. All right, don't worry, I'm not going to try to trick you with our examples with having to convert units. These are just standard units that we'll stick to for our course. All right, so we have the inflow of salt covered. The rate at which salt enters is this R sub I times C sub I. They both could be functions of time. In our examples, they'll generally be constants. So the inflow rate of solution and inflow salt concentration for our examples will be constant with respect to time. All right, let's take a look at the outflow part. And we're going to have similar quantities. It looks like algebraically or symbolically that we're just changing the subscript from I for inflow to O for outflow. But there's a bigger kind of a change here. The outflow of salt is coming out of the tank. Now, a concentration is an amount of something per, in this case, total volume. Now, the amount of salt can change as well as the volume. So what we actually get is an expression, a function, in terms of our quantities, A of t and V of t. The outflow concentration, and again, this is because the outflow is coming from within the tank, the outflow concentration will be the total amount, A of t, which we don't know yet, divided by the volume, V of t. All the units are still the same. And again, if we multiply the outflow rate by the outflow concentration, we get the rate at which salt leaves. We're going to replace the outflow concentration, C sub O of t, with that algebraic expression, A of t divided by V of t. All right, and we now have our kind of two ingredients. We have the inflow rate of salt covered, the rate at which salt enters, as well as the outflow. All right, and we just need to plug those in to our basic net rate of change formula. The left side is the derivative. Recall from Calc 1, derivatives are rates of change. And we're just going to replace on the right-hand side the two expressions above that we have boxed. Right, and if we do that, at the bottom here, we get what we'll refer to as basically the formula that we'll be using for all problems dealing with mixing or flow problems. All right, when you're ready, we're going to summarize that and point out some more details, but we basically have our equation or formula that we'll then be referencing for all future examples. All right, so let's take a look at an overview of what we just went through. So let's take a look at the formula for mixing problems. All right, first, this is an ODE, an ordinary differential equation for A of T, the amount of salt in the tank as a function of time. All right, first thing, the easiest case that we'll be dealing with is if the inflow rate and outflow rate are the same. Now, if the rate of solution entering and the rate of solution leaving are equal, that means the volume of water in the tank is constant. Almost all the examples that we'll be looking at within homework and the written assignments as well as in the textbook deal with this simplest case. Inflow and outflow rates are equal, which means the volume of water in the tank remains constant over time. All right, the harder case is if, of course, the inflow and outflow rates are different. And if that occurs, which might happen in kind of some examples in the textbook, as well as beyond our course, you might have to first solve for the volume as a function of time by solving this differential equation, the rate of change of volume. We again apply a net rate of change idea. The rate of change of volume of water in the tank with respect to time, this is going to equal the rate in minus the rate out, or the inflow rate minus the outflow rate. All right, and you can see above, if those rates are equal, the derivative would equal 0. If a derivative 0, that means the quantity is constant. So this is all consistent. All right, so again, this is the harder case if the inflow rate and outflow rate are different. The more important thing is while this equation looks very complicated, it's actually very easy to express it in linear form, which is the more important aspect right now to understand, since there's going to be a lot of different symbols within our lecture here and in the homework assignment, but they all have the same structure as what we were calling linear form. All right, the only change is we're denoting, instead of our independent variable as x, we're changing it to t for time. That just seems more natural for things changing over time. And we're going to change our function variable from y to a to denote amount of salt in the tank as a function of time. All right, so if we just basically add the one term from above to the left side, it's easily expressed in linear form. Our function is a, the derivative term is dA over dt. Now recall, whatever's multiplying your function term below in red, whatever's multiplying y in linear form, that's what we call and denote as p of x, which we need for our integrating factor. Well, here our function term is a. If this is in appropriate linear form with the function and derivative on the same side, whatever's multiplying a here is your p of t. And here, if you identify that, p of t would be r sub o of t divided by v of t. All right, when you're ready, let's take a look at a second example where we'll take a look at the easiest case where the inflow and outflow rates are equal. All right, there's a lot here. So pause, take a minute, read the question. I think I feel comfortable giving this as an example to all of you to try. Refer back to your mixing formula that we just derived and came up with. Scattered throughout this question are all the quantities that you need: the inflow rate and outflow rate, the inflow concentration, as well as an initial condition. So we did all the hard work in coming up or deriving that formula. Now we're just going to plug stuff in, rewrite it in linear form, and you can use a simple integrating factor to complete solving it as a linear equation. We'll check in a few minutes. All right, welcome back. In case you were stuck, let me give you a hint and do some of the translating for you. First off, the 20 pounds that is initially dissolved in the tank, that's the key word, initially, for your initial condition. That's going to give us an initial value. A of 0 equals 20. Since we're in a mathematics course, we'll leave the units off. Some of your science professors would be yelling at me for doing that, but we don't need no units in math. All right. Also, we're told the velocity, or sorry, the volume of water in the tank, which is 1,000 gallons. Since the inflow and outflow rate are the same, 5 gallons per minute, that volume of liquid in the tank is not going to change. So the volume of water in the tank will remain constant at 1,000 gallons. And the only other thing we need is the inflow concentration, which is given there as the 0.2 pounds per gallon, pounds of salt per gallon, if we're specific. All right, now with this, all we need to do is just plug it into our formula and just simplify it and rewrite it in linear form, add your A term to the left side, and it should be very simple to solve from here. If you were stuck so far in kind of translating the word problem above into your mathematical quantities and symbols, you should be able to complete and solve it from here. Identify P of T, get your integrating factor, and take it from there with solving it as a linear equation. We'll check in maybe another minute from here if needed. All right, welcome back. Hopefully you were successful from here. Let's check. So now that we have it in linear form, whatever's multiplying the function term, the function here is A, that's our P of T. So in this case, P of T is just the constant, 1 over 200. And that gives you a very simple integrating factor, a very simple exponential integrating factor, E raised to the 1 over 200 times T. All right, the work will continue on the next page. So with our integrating factor, mu equals E raised to the 1 over 200 times T. All the same steps apply here for solving a linear ODE. First, multiply the original ODE by your integrating factor. Do that on both sides. And the whole reason for using an integrating factor is the left side should collapse back to the derivative of mu times, not y anymore, but mu times the function variable here, a. And that is correct here. We get that the left side becomes the derivative of mu times A. And then on the right-hand side, we just have E raised to the 1/200t. All right, all we need to do is integrate both sides. And just be careful with kind of your integration on the right side there. A simple U substitution would work, or from my Calc 2 course, we might use what we call the 1/A shortcut. All right, and we can actually get a very nice explicit solution for A of t, like all examples with linear ODEs. After we integrate, we can just divide both sides by the integrating factor. And what we're using here is the very common alternate way to rewrite this. Dividing by an exponential, you can rewrite that as a negative exponential. E, in this case, raised to the negative 1/200 times t. All right, the only thing left for us to do from here is solve for the integration constant. We had our initial condition, A of 0 equals 20. And if you plug that in, E to the 0 is 1. And you should get C comes out to negative 180. All right, if we plug that back in, we get our explicit solution for A of t, representing the amount of salt in the tank at any time. All right, this was a standard example of what to expect for upcoming exam questions. Things in the homework are pretty much this straightforward. The only thing that's going to change are the specific values. Now, there might be one or two examples where the inflow and outflow rates are different, which would then mean the volume of water in the tank changes and is not constant. But here, the inflow and outflow rates were equal, both 5 gallons per minute, which meant that the volume was constant.